Uh, the talk that I'm going to present today is about efficient method that we propose for solving an inverse problem when the signal of interest is structured. So phase retrieval problem basically is the problem of recovering a signal X from its phaseless measurements, and it appears in lots of applications whenever it's hard or it's even impossible to measure the phase of the signal. It appears in crystallography, in optical imaging, in astronomy, and increase of resolution, which I'm gonna describe the last example in more detail in this slide. So it's quite usual to use microscopes to increase the resolution of our images. However, there is a fundamental limit for such increase known as diffraction limit. And this limit is proportional to the wavelengths of the wave that we use for illumination. And such a limit for visible light is around a quarter of micrometer, which means we are not able to capture molecular features which are of order of nanometers. We cannot use waves with higher frequencies either because of a couple of issues. First of all, reflectivity of such waves is so low and they are not suitable for systems which are based on reflection. Moreover, those high frequency waves has very high energy and they may deconstruct the object of interest before any image being captured. And to overcome these difficulties, one method that has been used for a long time is coherent diffractive imaging, or CDI in short, which I'm going to describe here. So we put the object of interest in a location and emit a group of waves toward it and record the diffraction pattern on a plane far from the object location. And with this diffraction pattern, we are able to take image of this object. But the point is we can only capture the magnitude of these waves, these diffracted waves, and hence we need to solve a phase retrieval problem to obtain the image that we are looking for. So let's formulate it mathematically. Phase retrieval is the problem of finding X from its phaseless measurements. In this display, X is a real or complex signal in high dimension. AI are known sensing vectors. They can come from a known distribution or they can be any fixed vector that with which we measure our signal. And epsilon I denotes the nodes, which usually assume to be Gaussian. But for this talk, I want to focus on noiseless setting. So from now on, I'm going to assume all epsilon i's are 0. So a few points about phase retrieval. First of all, the nonlinearity that we apply as the absolute value to our measurements makes the problem more challenging than a compressed sensing. One way to see this difficulty is to note that the problem is ill-posed. So if X satisfies our measurement equations, so does any rotation of the X. So we cannot detect a global phase for signal. No matter what method we use, because we cannot distinguish between these different solutions with our measurements. Even up to a global phase, having unique solution is more challenging than linear systems. So in 2006, Balan and his collaborator showed that for real signal in n dimension, 2n-1 generic measurements are required for having injectivity of this mapping of signal X to its measurements. They also discussed in complex case, 4n-2 measurements can be sufficient for injectivity. And later, Hinasari and his collaborators showed that asymptotically 4n measurements are necessary for having injectivity. Later, Banderia and his collaborator conjectured that 4n-4 is the right number, which is both necessary and sufficient for injectivity. They proved this conjecture for small values of n, but left it as a conjecture for general cases. Another difficulty we have seen in last couple of decades in the literature is whenever we want to consider the structure of the signal, the sample complexity or methods required to recover the signal are higher than information theoretic lower bounds or our expectations. So for example, if the signal is k-sparse, which means there are at most k non-zero entries in the signal, Actually, all but only one recent method that proposed so far require k-squared measurement for recovering the signal. While we have seen from uniqueness result, the measurements is expected to be linear in the level of structure. So we are going to discuss about this difficulty in later slides more. So for solving phase retrieval, there are a general strategy which includes lots of different methods proposed for this problem. So if we are using a non-convex method, the first important step is initialization, for which spectral methods are commonly used to find an initial point to start with. And the random matrix theory is the usual tool to analyze those methods. After having a good initial point, iterative methods are used to converge to the signal of interest. And in those methods, a stochastic gradient descent plays a key role, and non-convex optimization, concentration of measures are usual tool to analyze those methods. So for this start, I'm going to focus on the second step. So all I'm talking about, assuming we have a good initial point. However, I did some work regarding the first step, and I'm happy to talk about them offline if you are interested to know more. So one more thing that I want to assume for this start is our signal of interest is a structure. So we have seen different kind of structures among our signals. Sparse signals has been studied extensively. Low rank matrices have been studied as well. We also can have compressible signals. So for example, we can compress a natural image with much fewer bits than the original image without losing too much of the quality of the image. And if we use these structures for solving our problems, so in this case, we are interested in phase retrieval problem, we can increase the efficiency of our methods in the sense that we can decrease the sample complexity, we can decrease the time complexity, and we can improve the quality of our output. And this is all that this talk is about. So, as I said, sparsity has been studied extensively in the literature, but the point is sparsity is not enough to capture all the structure that we know about the signal. So, as you can see on the picture at the right-hand side, the wavelet representation of a natural image is in fact sparse. You can see lots of zero entries in this representation, but the sparsity is not the only structure that you see in this representation. You can note that the similarity between different blocks. So we need something beyond the sparsity to capture all the structure we know about the data, or at least more structure than a simple sparsity. Because of that, I want to adopt the notion of compressibility as the notion of a structure we're going to use in this start. And this notion of a structure has different advantages. First of all, compressibility is quite general. So all the structures that I briefly mentioned and many more structures that you can think of can be expressed as a compression method. So if you know some structure about your signal, you can store them in fewer bits than the original representation. This notion helps us to transfer the knowledge of compression community. So they've studied different signals. They have found complicated structures in different signals, and they proposed efficient method to compress them. And we can use this knowledge. We can transfer this knowledge to solve our inverse problem more efficiently. And one interesting fact about our proposed method is we can use them as a black box, by which I mean we don't need to know the details of the compression method or the structure that it uses. As soon as we are given a structure, as soon as we are given a compression method, we can use it to solve our problem efficiently, and we are going to see this in more details in later slides. So let me recall that we assume our signal of interest is compressible, by which I mean X lies on a compact set Q for which there is a compression method. So a compression family consists of pairs of encoders and decoders. Encoder maps our set Q to the points who can be represented by at most R bits, and decoder does the reverse in a way that error that we make as a result of this mapping is small. So this delta R is called the distortion of this compression pair. Uh, if you apply the encoder, you get a discrete set, which is called the code words of this compression. I think these pictures are quite clear that how a compression method is working. So because these concepts are kind of important for the rest of the talk, I probably pause for a moment here to see if there is any question before I move forward. Is it all clear? Okay, great. So recall that we are interested to solve phase retrieval problem, which means we have y1 to yn as our measurements, and we are interested to estimate signal x, and we assume x is compressible, and we are given a compression family with sets of decoder and encoder and the code word CR, which are introduced. A usual way to solve this problem is to define a cost function as the following. So this cost function measures the discrepancy of measurement at a candidate signal C from our true measurements. And by minimizing this cost function, we can have an estimation of the signal. But the point of our proposed method, COPER, COPER, by the way, stands for compressive phase retrieval, is it solves this optimization problem over the set CR. Because CR is a smaller set, much smaller set than the set Q or than the ambient space, we can solve these optimization problem more efficiently. What we are going to see in later slide is COPER has optimal sample complexity in some sense, which I'm going to describe. However, to get the estimation of COPER, we need to solve this optimization problem over the set CR, which potentially has 2 to the power R elements. This is a combinatorial optimization problem, which is hard to be solved. And to overcome this difficulty, we also propose gradient descent COPER, or GD COPER in short. So the idea is as follows. Recall that we reduce the problem of phase retrieval to an optimization problem to the set CR. And to make it practical, we just use a projective gradient descent to find this minima of our optimization problem. So we start with a good initial point Z0, and we update each step based on this rule. So in this display, PCR is the projection on the set CR. So at each step, we move toward the negative of the gradient of the cost function and project it on set CR. So at all steps, we remain at set CR. We proved that this method provably converges to the right signal, provided a good initial point and enough samples, which we are going to see details in next couple of slides. However, GD COPER has higher sample complexity in compare with COPER. So we are going to discuss this difference as well, and we are going to actually propose a solution for this suboptimality. So here is the first result we showed in our recent paper. Given our sensing vectors are coming from a complex Gaussian distribution, if you have a slightly more than this ratio in blue of samples, we proved COPER converges to the right solution with overwhelming probability. So this ratio, in the denominator, you have R, which is the rate of your compression, and delta R is the distortion that I introduced in the previous slides. And at the first glance, it may look strange, this ratio, but it turns out this is in fact a fundamental quantity, which I'm going to talk about it more. One more thing that I want to emphasize on this slide is note that we cannot recover a global phase of the signal, and that's why we measure the goodness of our estimate with this infimum. So we get the distance to the closest element of the class of solutions from our estimation. That's best we can do with the phase retrieval problem. And then the other constants are actually shown here. But the take-home message of this slide is we need a slightly more than this ratio as the sample complexity of COPER. We have a similar guarantee for GD COPER. So for sake of simplicity, we normalize all the vectors and elements of Q for this result. It's not a big deal. We discussed this in the paper that easily you can normalize everything that you have to deal with. And again, provided enough samples and close enough initial point, we prove this inequality. In this display, capital T denotes the number of iteration that we are in. And again, with high probability, we have this upper bound for our error. So note that as you iterate more and more, the first term goes to 0. And the second term is a linear function in terms of distortion, which you have full control over it. So you can in fact, determine the value of distortion even before you take any measurements. And hence, you can upper bound the error of your estimate as small as you wish. So one example would be to set distortion 1 over n. So specifically, if you're considering the problem in high dimensional setting and the signal's dimension is going to infinity, the distortion is going to 0. And then with this theorem, we have this much sample or squared samples to recover the signal. Because I want to compare the sample complexity with the one that we had with COPER, I'm going to write it down as the following. So if you ignore the logarithmic term in this display, what you can see is the sample complexity of GD COPER is a square of the sample complexity we had for COPER. And we are going to discuss this issue in more details later. So as I promised, let's see what this magical ratio means in our results. So note that the sample complexity of COPER is slightly more than this ratio. For GD COPER is this ratio square. To understand this, I'm going to study it in the asymptotic setting. So I'm going to send the rate of compression to infinity. And it turns out this quantity is closely related to box counting dimension. Box counting dimension is a notion to assign dimension to any subset of Euclidean space. So in this figure, what we are interested in is the boundary of this map. We are interested to assign a dimension to this object. What we do is we cover our object of interest with the grid with cubes, and we count how many cubes of length delta we need to cover this object. So n delta shows the number of cubes at length delta that we need, and delta, as I said, is length of the cube. And when you make your grid finer and finer, in the limit, you're gonna get one number as the ratio, as the limit of this ratio, which is going to be the box counting dimension of the set Q. There is a similar notion for compression family. It's called alpha dimension, and it's defined as the following. So alpha dimension of a compression family is lim sup of rate divided by log of 1 over distortion. So note that for the set CR, set of code words, we had 2 to the power R elements. So what you see here is nothing but the logarithm of the size of CR. And in fact, if you replace the grids that we had in the box counting dimension with balls, you'll see exactly the same thing. So with balls with radius delta R at centers of the points of CR, you can cover your set. And as you make this coverage finer and finer, what you're going to see in the limit is going to be something similar to the box counting dimension of your set Q. So to make it more intuitive, I'm going to give you some quantitative examples to see how this dimension matches with our intuition for well-known sets. So recall the definition of alpha dimension. If you consider the unit ball in n-dimensional real space, the alpha dimension of any compression method is going to be lower bounded by n. In other words, the unit ball has the full dimension. However, if you look at the k-sparse signals in the unit ball, alpha dimension would be lower bounded by k. And if you do the same thing, considering k-sparse signals in the complex unit ball, the alpha dimension would be lower bounded by 2k. And note that when you have a k-sparse complex signal, you have k real parts and k non-zero imaginary parts. Or in other words, you have 2k degrees of freedom, and that's why you see this factor of 2 here. So as I said, in this slide, one signal of interest that we are going to focus on is our natural images. One might ask, what is the alpha dimension of these signals, natural images? So this is interesting question, but it's hard to be answered quantitatively, but there is a good intuition for that. The intuition is as follows. So natural images lie on a low dimensional manifold over the space Rn or Cn. And the alpha dimension would be lower bounded by the right dimension of that manifold. And that's exactly why we are claiming the sample complexity of COPER is optimal. I'm going to discuss it more in this slide. So again, recall the definition of alpha dimension and the fact that COPER needs a slightly more than this ratio, or in limit, a slightly more than alpha dimension of our compression family to recover the signal. To make it simpler, just think of k-sparse signals. So as I said, alpha dimension for efficient compression method for k-sparse signals is going to be k, and COPER needs a slightly more than k measurements to recover the signal. So note that k measurements is even needed when you're solving a linear system, and COPER solves a harder problem, a problem in which you are not observing the phase with the same number of measurements. And that's optimal. Basically, that's in the definition of alpha dimension. That's the minimum number of measurements you need to have a good approximation of your signal. But as we discussed, this sample complexity for GD COPER is not optimal. In fact, it is proportional to the square of alpha dimension up to a logarithmic factor, which shows us there is a room for improvement in the COPER. And in fact, we use the theory that we developed to analyze GD COPER to solve this issue. And I'm going to come back to it in the very last slides. But before moving to that, before moving to the suboptimality of GD COPER, let me show you some simulation results. So the simulation we run was on natural images. So the signal of interest is an image. We start GD COPER from a completely white image or any random image, irrelevant from our signal, which we don't know that. And we run GD COPER by using JPEG 2000 as our compression method. The way that we are going to evaluate our estimation is by two quantities. First one is normalized error, which I wrote it down here. The second one is PSNR, peak signal to noise ratio, which is a logarithmic function of the error. One more thing that we are interested in looking at is the ratio of sample size to the dimension of the X. So we are interested in how many samples is in fact required by GD COPER to recover the signal. And hence, this is an important quantity in our later slides when we are discussing the performance of GD COPER. So basically, this is what you are going to see in later slides. These two curves shows the normalized error and PSNR for one run of GD COPER. You can see our signal of interest here, and you can see the result of very first steps of GD COPER. So note that even after 6 steps, the estimation has a strong correlation with our signal. By the way, the horizontal axis corresponds to each step. One more thing that you might note from this curve is, let's say after 20 steps, when your PSNR is above 30, you have more or less perfect estimation. So you cannot note the visual differences between this estimation and the image that you had initially. So in order to compare the performance of GD Cooper and show you what the consideration of structure offers us, I compare it with a well-known method to solve phase retrieval problem known as vertical flow. So vertical flow was introduced by Candace and his collaborators in 2015. It's more or less similar to GD Cooper, except for the fact that they solve phase retrieval for generic signals. They don't take the signals structure into account, and they have shown in their paper that vertical flow needs to be oversampled to find the true signal. So in the first comparison that I want to show you, we are in the undersampled case. So the number of measurements that we have is the half of signals dimension, as you can see here. So as you can see from the normalized error curve, vertical flow cannot find the signal of interest in this case, while GD Cooper does pretty well. So after a few steps, it gets error less than 20%. As you increase the number of measurements, still vertical flow cannot find the right signal, but of course, GD Cooper's estimation gets better and better. Even when you have the same number of samples as the signal dimension, vertical flow cannot solve the problem. And note that this is still counted as the undersampled case because our measurements are phaseless. We don't have the full data of a linear actually mapping of our signal. So this is still undersampled case. But as soon as you oversample the problem, both GD Cooper and vertical flow are able to find the right signal. However, as you can, as you probably noticed that GD Cooper does it much faster and fewer steps. So here is another report from the same simulations that I've shown you different figures before. First row of these figures shows the final output of GD Cooper. The second row denotes the final output of vertical flow for different samples to dimension ratios, which corresponds to the columns. So as you can see, in all cases, vertical flow, GD Cooper's estimation has a strong correlation. Of course, it gets better as you get more samples, but even in sample cases, it output estimation with strong correlation. This table also gives you more detail about that run. One thing that I want to call your attention about is in the oversampled case, which corresponds to the last row of this table, while the quality of estimation of vertical flow and GD Cooper is more or less the same, GD Cooper finds it in much faster. So it runs in almost 30 seconds, while vertical flow needed 140 seconds to output this speed. So let me quickly come back to the suboptimality issue that I talked about for GD Cooper and the root of this suboptimality. So recall that we defined this cost function and we wanted to optimize it, minimize it, in fact, to find the estimation of our signal, and we adopt a projective gradient descent to do so. So because of additive form of the cost function, your gradient is going to be in this additive form. And to bound the error of each step of GD Cooper, I need to bound the deviation of gradient from its expectation, which eventually is going to be in form of sum of WIs minus its expectation. One thing that I want to call your attention is each terms of this cost function is more or less like a Gaussian random variable to the power 4. So AK is a Gaussian vector. You project it on the direction of C and you raise it to the power of 2 twice. Because of that, when you project each vector involved in the summation of the gradient at the direction of x or any other direction, what you're going to see is going to be it's going to be more or less like a Gaussian random variable to the power 4, which has a heavy tail. And as I discussed here, we are interested in the concentration inequality for such heavy tail distribution. And this is in fact the root of suboptimality that we have seen. So to formulate it more accurately, I'm interested in bounding the probability of deviation of such sum from its expectation in terms of deviation amount epsilon and the sample size n. So we have n number of WICL. And for simplicity, I just assumed WI or IID with heavy tail, which we discussed before. So I need to define the rate function to present our results in this case. So rate function is basically the negative log of the tail of the common distribution we are interested in. And the point is, for sub-Gaussian and sub-exponential tails, there are a very sharp and good concentration inequalities. But this is not the case for heavy tail distribution. So as soon as your rate function gets sublinear, we didn't have a suitable inequality so far until recently that a few papers came out. And one of them is the result that we in fact developed for analysis of our proposed method. So recall the definition of rate function, the negative log of the tail, and the fact that we are working with heavy tail distribution, which means rate function is sublinear. So one thing that I want to note is it's easy to get a heavy tail distribution. Basically, if you raise the normal distribution to any power greater than 2, you're going to have a heavy tail distribution. And an important fact about this distribution is moment generating function is not finite at any point when the tail is heavy. And as I said, except until recently, there were not any suitable concentration inequality that we were looking for. So this is another result we published in our recent paper, in a different paper, which gives us the bound on the probability we needed. So let me note that we centralized our random variables. So basically, this deviation is the same thing that you have seen before, except for the fact that expectations are 0. And we upper bounded this probability in 2 different regions. So for large deviations, when epsilon is larger than a threshold, we have a concentration inequality based on the rate function. And for a smaller deviation, you're gonna see a bound more or less similar to the Gaussian tail based on the deviation amount and the sample size n. So I don't want to go to the details of this result and the proof of it, but I just want to note that we proved this concentration inequality is sharp, and because of the sharpness that we had for this bound, we in fact proved with the same cost function we used for GD COPER, no matter what methodology you use, for bounding the error of gradient, you're gonna need alpha dimension squared of measurement. And there is no artifact of our analysis or anything else. With this cost function, you're gonna need this sample complexity. And hence, the only hope to get optimal sample complexity is to change the loss function that we discussed. So note that we faced heavy tail distributions because we raised our measurements to power 2 twice. One natural alternative is to replace one of these squared with absolute value. And if you do so, you get back to the class of sub-exponential tail. And with a simple Bernstein inequality, you can get a sharp concentration inequality that we required. And in fact, we have shown with this cost function, GD COPER is going to need a linear number of alpha dimension as a sample complexity. However, this result is not published yet. It's still an ongoing project, and we are still working on different aspects of that. So that's all I wanted to talk about today. Thank you for your time and for your attention. Let me know if there is any question.